Good afternoon once again. So yesterday we were learning regarding the color of coordination compounds. There a little more. Just let me tell you. Okay. So what was that is color of coordination compounds. In this I told you the d electrons if it is 1 and if it is 9, 1 to 9 if it is there, definitely it will have one or the other unpaired electron, and that unpaired electron when it absorbs energy it shall go to the higher energy, and that higher energy is not permanent, again it shall come back to its original level. So while it is coming back, it will radiate out whatever absorbed energy is there, and that will have some wavelength and frequency, and that will be the color that shall be observed rather. Okay. Now further, uh, white light is meant to fall on that substance, the coordination compound. And in that white light, you know very well, in the physics you learn, so it's a mixture of 7 colors. Okay, violet, indigo, then blue, green, yellow, orange, red, like that it is. Okay, so it shall be absorbing all the colors and it may not be absorbing one of the colors. What it does not absorb out of those 7 colors, what it does not absorb out of the 7 colors, that it shall be emitting, and that is what we are seeing it as the color. Okay, so D1 to D9 which has got unpaired electron, at least one unpaired electron will be there, and that unpaired electron helps in the exhibition of the color. Okay, helps in the exhibiting the color of the coordination compound. And if it is D0 configuration or D10 configuration, no unpaired electron. Okay, no unpaired electron shall be present. No unpaired electron. Since no unpaired electron, it shall not be color. No color is being exhibited, and this shall be color. Now, out of that, whatever the Vibgyor colors are there, out of the 7 colors, so whichever it is absorbing, it shall keep it. Whichever it is not absorbing, that it shall be emitting, and that is what we are seeing. So here we have another thing to know, that is complementary colors. Complementary colors. Taking one example, let us know COCl NS3 5 times 2 plus. COCl NS3 5 times and 2 plus. Okay. Now this is absorbing some color, absorbing, and the complementary color to that absorbed color is which one? Which shall be exhibited. Okay, complementary color, absorbing color and the complementary color. So here it is going to absorb the yellow color. It absorbs yellow color and it gives the complementary color to the H2, CONH3 5 times and H2. Okay, naming you can try, right? So here this is absorbing blue-green color. This is absorbing blue-green color. And this is emitting, this is giving which color? It is giving the red color. For the blue-green, the complementary color is red. The next is CONH3 6 times. CONH3 and 6 times. CONH3 6 times. So it is absorbing blue color. It is absorbing blue color, and the complementary color to this is yellow orange. Yellow orange. Yellow orange. Just have a look. Another 2 examples are there. Then COCN6. COCN6. Okay, COCN6 3 minus. Now this does not absorb in the visible region, but it absorbs in the region. And whatever the complementary color to the ultraviolet regions frequency is there, it shall be pale yellow. Pale yellow. You need to just remember this concept. Remember this colors and complementary color. If you are remembering and able to reproduce, very fine. Okay, but if not, not that much of very important. So, but if you remember, excellent. Then the last one, COH2O 4 times. H2O 4 times 2 plus. Okay, then this is absorbing red color, and the complementary color to this red is blue. That's why, see, you must have learned complementary colors. Which color will appear brightest against what other color? Okay, for red color, blue is the opposing, the complementary, the contrasting. So red, it is absorbing, blue color it is giving. So this was regarding the color of the coordination compounds. Then coming to stability, stability of the coordination compounds. That's stability of coordination compounds. To what extent are they stable, and what makes it stable? What basis we call it as stability? Now suppose one metal ion is being bonded with 4 ligands, and then what will be the molecule formed is ML4. Okay, ML4. Okay, so this is what is the molecule that shall be formed. One metal atom is bonded with 4 ligands, let's say, and it is going to form ML4. Now this ML4 to be formed, you have several steps, remember. Not all the 4 ligands will be bonded with the central metal atom at once. So what are those steps involved? Okay, one metal atom, this is the first step, will bond with the one ligand and it forms Ml. Now here the stability constant is given by K1, and that is given by what? Molar concentration of, it is Ml, okay, the product, divided by molar concentration of metal into molar concentration of ligand. Let us say it is K1. So this is Ml is being formed in the first step. So it's something like mechanism. Okay, in the mechanism you have several steps there. In the next, so this Ml will undergo a bonding with another one more ligand. One more ligand is going to bond. That time it shall be Ml2. So whatever the stability constant is there, it shall be Ml2 divided by M into L. Okay, divided by M into L. Stability constant. Okay, a little mistake. Ml into L. Molar concentration of Ml. This one into L. It will keep on increasing. One by one, it shall be increasing. So this is K2. Further, third one. Ml2 will be there, that shall bond with another ligand. So this time it will be Ml3. So it will be, stability constant will be K3, and it is Ml3 divided by Ml2 into L. Ml2 into L. Fourth one. Okay, this is stability constant, third step, third whatever the step is there. Then Ml3 plus L. So this will be Ml4. So you get this finally. So what will be this? K4. K4, and that is equal to Ml4 divided by Ml3 into L. Ml3 into L. So here the final stability constant, it is given by Bn, beta N. Stability constant, it is given by beta N. So it is based on this. It is based on this. So it will be Ml4 divided by the metal, molar concentration of metal into molar concentration of the ligand we have. Molar concentration of the ligand L raised to 4. So now, but this whatever the step is there, it involves several steps. It's not one step reaction, it's a several step reaction. So what will be beta n then? For this reason, beta n is going to be K1, the product of all the stability constant. Okay, product of K1 into K2 into K3 into K4 and so on. K1 into K2 into K3 into K4 into so on. If at all there are n steps involved, it may go up to the nth step. K1, K2, K3 up to Kn. Okay, so this is what is stability constant. And further, if you take 1 by K, 1 by K, okay, so the reverse, so the reciprocal of that is called as the instability constant. That will give you to what extent it is unstable. Instability constant. Okay, it has not been asked, but it is in the syllabus. For that reason, we have to learn regarding the stability of coordination compounds. Metal and the ligand is bonded. 4 ligands are bonded. There may be 6 ligands also. So you may go for another 2 steps that time. So one by one ligand is going to bond, and one by one K1, K2, K3 up to Kn, whatever the number of ligands are going to be bonded, you have that. So the product of all these stability constant will give you the beta n, the total stability constant, total stability of that coordination compound. It will tell you to what extent by k if you take, okay, that shall give you the instability constant. Just have a look. Okay. Next. The next is factors affecting the stability constant. Factors affecting stability constant. Factors affecting stability constant. Okay. So what are the factors on which the stability is dependent? First is the higher charge of the central metal atom. Higher charge of central metal atom. Central atom, that is metal atom. Higher charge of the central metal atom. Okay. So greater ionic means why it should be higher charges. When it has got higher charge, it will attract the number of ligands, and when it is bonded with number of ligands, more will be the stability. Okay. So greater ionic potential. So here what is going to be told is, so what is the meaning of higher charge of the central metal ion? It shall be greater ionic potential. Greater ionic potential is there. And this greater ionic potential, it is given by what? It is given by ionic charge by ionic radius. Ionic charge by ionic radius. It is given by ionic charge by ionic radius. And greater will be the stability. Higher the charge meaning, so higher the greater ionic potential will be. Greater ionic potential is nothing but the ionic charge by ionic radius. If you take, it is higher side, and if it is higher side, the stability is more because it shall be bonded to more number of ligands. The second point is greater base strength of the ligand. Greater base strength of the ligand. Greater base strength of ligand. So when it has greater base strength, greater will be the stability. So it shall be donating sufficient number of electron pairs, and it shall be creating number of bonds between the central metal atom and the ligand. So more number of bonds, definitely the stability shall be higher side. So greater base strength of the ligand, stability is more. Stability is going to be more. So more donating capacity of the electrons, more stable is the compound. Third one, you have chelating ligands. Chelating ligands. Those chelating ligands are what? These are ring forming ligands. Ring forming ligands. And these ring forming ligands, okay, ring forming ligands, they'll definitely have number of donating sites. So it's a polydentate ligand. When it is a polydentate ligand having number of ligating sites and ring forming, so definitely that's a ligand. And so chelating ligands, they produce more stability compared to the other ligands which are not chelating, which are not ring forming. If you compare the chelating ligands, they produce more stability, or they stabilize the coordination compound to a maximum extent. Then there are what we call multi-dentate ligands are there. Polydentate ligands also we can say. Okay, multi-dentate ligands are there. Multi-dentate ligands. These multi-dentate ligands happen to be cyclic without any steric effect. Sometimes, because there are many dentating sites, many donating sites of the electrons are there in the ligands. So they can be surrounding, they can be forming a ring around the central metal atom without any steric problem there. Okay, since there are many ligating sites, many donating sites of the ligands. So what shall happen? So it is going to bond the central metal atom from all the possible sides. When it bonds there from all the possible sides, almost it forms a ring like a structure. When it forms a ring like a structure, and that becomes sufficiently stable. So such a effect, multi-dentate ligands, so they form cyclic. Okay, they form cyclic without steric effect. Without steric effect. Without steric effect. Cyclic, it is going to form a bond without the steric effect, and such a effect where we have polydentate, not the chelating, you have polydentate or a multidentate ligand which surrounds around the central metal atom and forms the bond with the central metal atom. Okay, so without any steric effect, it is called as the macrocyclic effect. It is called as the macrocyclic effect. Macro means there are many ligands which are going to bond with the central metal atom. There are many ligands which are going to bond with the central metal atom. That's why the word macro, and almost it's going to be cyclic in form. That's why cyclic, macrocyclic effect. This is not chelating ligand, but without chelating nature also, it is able to form a strong bond, and that gives rise to a stability in the molecule. Okay, just go through. We'll go to the bonding in metal carbonyls, synergic we say. Okay, next, bonding in metal carbonyls. Bonding in metal carbonyls. Now, in this bonding in metal carbonyls, what do you have? Between the metal and the carbon monoxide rather, there is going to be a sigma bond also, there is going to be a pi bond also. Sigma bond is formed because of the electrons being donated by the carbon atom to the empty orbitals of the metal. Sigma bond is formed because of the electrons being donated by the carbon atom of the carbonyl to the empty orbitals of the metal atom. Then pi bond is formed, okay, because of the electrons which are present in the metal, which shall whose orbital shall overlap with the carbonyl's empty orbitals. Okay, so there actually the pi star or anti-bonding orbital is involved there. Pi star anti-bonding orbital is involved in the between the metal and the carbon to form the bond, to form the pi bond rather. Such a bond we also call it as a synergic bond. Okay, let us see. Now one metal atom is here in the center, and it has got various orbitals like this. And there is carbon monoxide, carbon monoxide. This has got its own orbitals. Okay, then even this carbon, it has got empty orbitals like this. Now there is another orbital. Okay, now here this is carbonyl, this is metal. This is the empty, this is the vacant orbital of the metal. That's the vacant orbital of the metal which is going to receive the electrons from the carbon. So here there are electrons present. So those are going to coordinate bond. Those are going to have a coordinate bond with the empty orbitals of the metal. So this shall give rise to what? This shall give rise to sigma bond. That will give rise to sigma bond later. Now there are electrons in the orbitals of the metal. Okay, pi star antibonding, what you learn in the case of the chemical bonding. Okay, so these are going to be donated. These are going to be donated to the empty orbitals of the carbonyl. That is carbon only, not carbonyl. To the carbon it is given. So here the pi star antibonding orbitals are involved. Okay, so pi bond and pi bond is going to be formed here. Okay, and sigma bond because of the electrons being donated from the carbon towards the metal. Pi bond because electrons are donated from the metals whatever pi star antibonding orbital is involved, and the p orbital of the carbon atom, and that will give rise to pi bonding. So this kind of bonding, because both are donating, both are sharing their extra electrons with the other, such a bond we call it as synergic, cooperative, synergy bonding is. Okay, both are donating here. Carbon monoxide also, metal donates in the empty orbitals of the carbonyl, carbon donates in the empty orbitals of the metal. Such compounds are how many? Okay, different examples are there. NiCO4, nickel tetracarbonyl, nickel tetracarbonyl. It is a tetrahedral structure. This one, it shall give rise to a tetrahedral structure. Further, FeCO5, FeCO5, iron pentacarbonyl, they say. Iron pentacarbonyl. This iron pentacarbonyl, it is TBP structure, trigonal bipyramidal structure. Trigonal bipyramidal structure. CrCO6, chromium hexacarbonyl chromium. This is octahedral structure. This is octahedral structure. Further, you have Cu, cobalt octacarbonyl, cobalt octacarbonyl, cobalt octacarbonyl. So Cu2 it is, CO2 and CO8. Now this structure is something like bridge structure. You have structure like this, cobalt, cobalt, and again cobalt. Further, there is one bridge carbonyl, another bridge carbonyl, then remaining three carbonyls are there. 1, 2, 3. Here also 1, 2, and 3. Okay, a kind of bridging molecule, CO2, CO8. This will be capital O, capital C. These two, okay, these two. I'll circle it with the red. Those two will be cobalt. This and this. These two are cobalt. The remaining all are the carbonyl, carbon monoxide. Okay, this kind of structure will be getting a bridging kind of a structure there. Even for Mn2 CO CO10. Mn2 CO10 also will be getting a similar structure. So this is regarding the bonding in carbonates, metal carbonates. This is important. Synergic bonding. Carbonyls, carbon donates electrons to the empty, to the vacant orbitals of the metal. That is one. Metal atoms, whatever pi star antibonding orbital is there, that shall overlap with the empty orbital of the carbon, and there will be a pi bond that which is present. There is going to be a pi bond that which is present. Okay, so using the pi star antibonding orbital, it shall be bonding there. So that is what is the synergic bonding. Then coming to the one or two disadvantages of the crystal field theory. Okay, so it is taking into account that ionic bonding is considered. So covalent bonding, if it is considered, there the crystal field theory is failing. Okay, crystal field theory fails. Then it says only the anions are found at the low. Okay, found at the low and low end of the spectrochemical series are going to bond like that. So that is another drawback. Anions are found at the lower end of the spectrochemical series. That is another drawback that we have in the crystal field theory. Now let us go to the last part, that is the application That is the user's part of the coordination compound. Just have a look. Importance and applications of coordination compounds. Applications only we learn. Applications of coordination compound. First one. You know, in the hard water there are calcium and magnesium ions present. Okay. So in hard water you have calcium ions and magnesium ions. So to what extent it is present? Because WHO standard says more than 500 ppm of hardness is not good for the human health. So it should be less than 5 ppm or 500 ppm. Okay. So you need to check how much it is. So using what you can check is sodium EDTA you can check. Sodium EDTA titration. What is that? EDTA is ethylene diamine tetraacetic acid. Sodium ethylene diamine tetraacetic acid titration in the basic buffer medium around the pH 10 using ammonium chloride and ammonium hydroxide. So you can adjust the pH value there and do the titration. What shall happen is calcium and magnesium ions will form a coordinate bond with the EDTA. Sodium ions go into the solution. So there you come to know how many calcium ions and how many magnesium ions are present, and together the total count will give you the total hardness in water. So in Gulbarga city, this can go for one mineral water, any plant, there also you can get some water and it will be doing. So here EDTA is a ligand. So sodium EDTA, sodium will replace the calcium and magnesium ions. So this is one. Next is in the extraction of metals. In the extraction of metals also you require complexing agent. Extraction of metals. Silver and gold especially. Okay, silver and gold if you take. So these are going to complex leaching method we have learned. When I was telling you regarding metallurgy, I have told you how the gold ore is separated from its gangue, that is by leaching. So sodium cyanide is being treated there. That cyanide forms a complex with the gold cyanide, then gold chloride conversion, and then you take for the further processing to get the gold material. So in the extraction of metal, especially silver and gold, so you are using the complexing agent. It will depend from place to place. Not at all the places every substance is suitable, because the gangue material may be different. The nature of gangue may be different. So that's why established itself the process may not be there. Some changes you will have to do there in order to get the metal or the whatever the important mineral is there. Okay. Then is purification of metal. Okay. Third is in the purification of metal also you require this coordination compounds. Purification of metal. So actually if you had learned the metallurgy lesson, these few of the examples should have been clarified. Impure nickel will be there. So that impure nickel will be converted to nickel tetracarbonyl. It will be converted to nickel tetracarbonyl, which is a coordination compound. Later, this nickel tetracarbonyl, which is decomposed, okay, this shall be decomposed. Decomposition we do, and there carbon monoxide shall be removed, and you get only the nickel. Okay, carbon monoxide will escape out, and you get the nickel. So whatever other impurity is present, that shall be removed by complexing, by coordinating the carbon monoxide with the nickel. This process, it is called as a Mond's process. You'll find it in the books. Okay, NCERT book, metallurgy topic. This is there. Okay, Mond's process of purification of nickel. So here, carbon monoxide is used as a complexing agent in order to separate the nickel from the remaining whatever other impurities present. Later, that nickel tetracarbonyl is taken for decomposition. So you'll be getting nickel and the carbon monoxide. Carbon monoxide is a gas, it shall escape out. So then further, very important is in the medicine field. Okay, so suppose some metal ion is being present in our body, like copper is there, iron is there in our body. Those can be removed by complexing. Iron in the colloidal form, it should be present, it may be required, okay, for our body, but in the some other form if it is present, it may be dangerous, okay, so it may be poisonous, so that should be removed. So that is removed by the complexing method. So there are some two medicines, like so in the medicine field. Next is in the medicine field, especially for animals and plants. Okay, for animals also, plants also. Animals and plants. So if at all there is copper or iron, okay, copper or iron is going to be present as a contaminant in our body. So it can be removed by chelating method, removed by chelating process. It shall be removed by chelation. Now, which are the chelating ligands? So you have dipensylamine. Okay, dipensylamine. Penicillamine. And another is desferrioxime. Desferrioxime. Okay, desferrioxime B. Desferrioxime B. These two are the agents which can form a complex, which can form a chelating complex, a ring form of the coordination compound with the copper and the iron. Once it forms a chelating complex coordinate with the whatever the copper and iron, it shall be flushed out of our body. So that's how the extra contaminant like copper, iron can be removed by this dipenicillamine and desferrioxime B. So these are complexing agents. These will form a coordinate bond with the copper and iron very strong. Then in the hydrogenation of alkenes. Next one. Have a look, okay? I shall give you time. Fifth one, okay. So in the hydrogenation of alkenes, hydrogenation of alkenes. In the hydrogenation of alkenes, there is one rhodium coordinate compound, rhodium complex. They say it was discovered by Wilkinson. Okay, that's why it is called as Wilkinson's catalyst. PPS3 RH PPH3 triphenyl phosphine. PPS3 thrice, then RH and Cl, rhodium catalyst. Triphenyl phosphine, rhodium chloride. Okay, so this is also called as the Wilkinson's catalyst. Wilkinson's catalyst. Wonderful this is. Only one also, if you learn something in the chemistry, you can make your living. I'll tell you this, what it is, the meaning. Catalyst you have to get for conversion of alkenes to alkenes, hydrogenation of alkenes. C2H4 is there. You hydrogenate it, you'll be getting C2H6, which is ethane, and ethane is a fuel. You can make fuel, and you can definitely get the license and start selling. You can make your living. Okay, nothing big we need to do. So Wilkinson's catalyst will help in this conversion, hydrogenation of alkene to alkane. And alkanes, most of the alkanes are very best fuels. Okay, the last one. Okay, again it is used in the medicine field. The platinum complex, cisplatin they say. Platinum complex, that is cisplatin. Cisplatin. Cisplatin they say. Cisplatin is PT, NS3 2, NS3 twice, Cl. Okay, PT, NS3 twice, Cl2. This is used in treatment of cancer. Cisplatin. Okay, this is a complex, a coordinate complex of the platinum with the ammonia and the chlorine in the cis form, not the trans form again. Okay, it is used in the treatment of cancer. Now don't feel, sir, I know now cancer tablet, I'll give cisplatin pure. Not like that. So this in what form? Okay, colloidal form, tablet form, along with this some other thing may be required. All that together it will be given, and that's how it will be help in the curing of the or removal of the tumor, the unwanted cells in the body. Okay, so this is one of the medicinal use of that cisplatin. Cisplatin is the cis isomer of the platinum with the ammonia and the chlorine. Okay, cisplatin, that is platinum complex with the ammonia and the chlorine. It shall be used in the treatment of cancer. Okay, with this I at least wind up with the syllabus. I think within 1 or 2 days we shall post one of the question paper, the whole syllabus question paper, and within short time I think you'll be having a full syllabus test also. They'll let you know on the WhatsApp group. So keep learning. Post your doubts if you have anything on the group. It shall be clarified definitely. Okay, or even I think you have our personal numbers also from that group. Using that also you can put it and get your doubts clarified. Okay, get your doubts clarified then. Okay, thank you for watching. Have a nice day.